example, we want to find the electric field at a point P due to a large charge Q, due to a charged rod with total charge Q and length L. Point P is going to be a distance y above the midpoint of the rod. So when we do these problems, the very first thing we do is we identify a little bit of charge, which we call dq. So it's the charge element on the rod. So we identify dq. Let's label that on our picture, dq. And then what we do is we know dq is a charge, therefore it makes an electric field. The electric field it makes at point P is going to go straight outwards from it because it's a positively charged rod. So it makes an electric field that points out this way. This is a little bit of charge, so it makes a little bit of field, which we'll call dE. There's our electric field vector. Let's break this into components because it is a vector, so it has components. Our x component here points to the left. There's dEx, and our y component points up. There's dEy, dEx. So now what we want to do is let's write down what is dE. So our total electric field E that we want to find is going to be an x component in the x direction plus a y component in the y direction. Our x component of electric field, Ex, is going to be the sum of all the dEx contributions. So we take this rod, this charged rod, little bits of charge all the way along. Each one of them makes an electric field with an x bit and a y bit. When we add up all the x bits, we get the total x. When we add up all the y bits, we get the total y. So here, before we go any further, before we get into the calculus, it's not a bad idea to ask, does anything cancel? And again, if you don't get this by looking at it, it's okay. When you do your integral later on and you put in your limits, you will see that it sums to 0. So let's think about our charge. The charge on this side of the rod has an x component that points to the left and a y component that points up. If we thought about a piece of charge right here, so the same distance from the end but over on this side, this would make an electric field that points this way. It would be up and right. So this x component would point to the right and the y component would point up. The part of this electric field that pointed right would cancel with the part of the electric field that pointed left here. The y parts, they both point up, so they wouldn't cancel at all. So for this side of the rod, all the x components are to the left and all the y components are up. For this side of the rod, all the x components are to the right and all the y components are up. That tells us that the x components are all going to cancel. And now if you didn't catch that, you could go ahead and you could do your calculation and you would find that your answer would be 0. Maybe that's not a bad thing to try as a bonus. So now, if we want to find the y part, let's start to sort out how are we going to find our y values. So our y component of electric field, so we have a vector here. To find our components, we need to put in an angle and think about sine and cosine. Let's call this angle theta, which makes this angle theta. Our y component is opposite our angle, so we'll need to use sine to find the y component. So dEy equals dE times sine theta. Okay, now we have to start sorting out what are we going to fill in for the different parts. So dE we know is k times dq over r squared. Okay, those have things we have to fill in. K is our constant, 8.99 times 10 to the 9 newtons squared meters squared over coulombs squared. dq is our little bit of charge here, and r squared is our distance between our charge and our point. So on our diagram, from here to here is our distance r. Let's look at what r is. This distance is y. Let's put in a coordinate system. So let's put our y-axis here. Let's put our x-axis here. So here's our origin right here. So So then from the origin to our little bit of charge, that distance is going to be x. So then r is the hypotenuse of a right-angled triangle where the legs are x and y. So r squared equals x squared plus y squared. If you wanted to write down what r was, you would say that r is x squared plus y squared to the 1/2. So there's something for r. Now we have to think about dq. We know as we come along the rod, the thing that's going to change is going to be the x value. Y is always our distance above the rod. It's always the same value, but this x is going to change. When it's all the way over here, it's half the length of the rod. When it's here, it's 0, so it changes. When it's here, it's minus L over 2. So x is going to change, so we'd like to write down dq in terms of our variable x, because that's what we're going to have to integrate with respect to. So dq is an amount of charge in this charge element. If we want to know the amount of charge, what we can do is we can multiply the charge density, lambda, times the length of this charge element. And this charge element is a little bit along the x direction, so it has length dx. Okay, let's just kind of go over that quickly once more. So we know that charge density is charge divided by length. So anytime we wanted to find an amount of charge, we would do the density times the length. So in our problem, the amount of charge we're trying to find is dq. The amount of length of this charge, if we were looking at the whole rod, it would have length L. We're not looking at the whole rod, we're just looking at a tiny bit of it. The length is dx, and we use dx because it's horizontal. If it were vertical, then the y part would be changing and we'd use dy. But this is a little bit in the horizontal direction, so the length is dx. Density has the symbol of lambda, and it's charge over length, so the total charge is q, and the total length is L. So that's where this expression right here comes from, dq is lambda dx. So that's our dq. We also want to know what is sine theta, so let's write that part down as well. So sine theta is equal to opposite over hypotenuse. In our picture here, y is the opposite, and the hypotenuse is r. But for r, we said it was y squared plus x squared, take the square root. Okay, so those are all the ingredients we need to put into this expression, so that's the part we'll do next.